Thank you, Sueli, for the very kind introduction. It's really an honor to be here in front of you, and I'd like to thank the organizers of this school for this invitation. I understand that the first lecture in the afternoon is always a little bit difficult because we have to compete with other feelings. And I hope that I can attract your attention for the next hour and a half or so. By the way, this is really a presentation for you, so please, you can interrupt at any time and to ask questions. No questions are silly questions in this subject. Sometimes the ones that perhaps may look a little bit like odd or extravagant is the one that finds new ways, new paths. So please give way to your questions. I understand that we have a pointer here, right? So maybe I should use this pointer and try not to block the view of the colleagues over here. Okay, the formal name of this, of course, it's an introduction to information theory, but I like this name because it sort of tries to represent my intention of making available a good portion of the book by Cover and Thomas, that's now a classic in information theory, in a set of 2 lectures of an hour and a half. So I think it's going to be difficult, but of course I had to be very selective on the subjects and try to really include only the material that I thought would be fundamental and basic for the understanding and perhaps the creation of new technology in this area. And I also like the it, when we talk about it, what is it? Well, you know what is it, right? So everything there is in a nutshell. Okay. So some of the summary, perhaps a little bit ambitious, but we'll try to cover all this material. You'll see that these are chapters in the book by Cover and Thomas. We'll have a brief introduction, and then we're going to talk about 3 quantities that are central to information theory. Really central. And entropy, the Kullback Leibler divergence, and the mutual information. In fact, a good portion of our presentation is going to be on this second topic here. And then we'll start with some applications. Data compression, source coding, and the dual of it, which is channel coding, transmission over unreliable channels. These 2 subjects, transmission of unreliable channels and data compression, were in the initial paper that started this whole thing, that started it. The initial paper by Claude Shannon, 1948. It's difficult to think of an area that was really started out by the vision of one man, and in particular with one paper. And we'll see a good portion of what we'll cover will really be on the dealings of Shannon on that very first paper. And then we'll look at differential entropy, which extends the notion of entropy to random variables that are continuous. And we'll look at the Gaussian channel, a channel that's very much used because it represents, well, something that happens, for example, in deep space communications. And then we'll look at the true dual of channel coding, which is rate distortion theory. In the first part, data compression, we'll look at it from a preliminary perspective. And then when we go deeper in, we'll have the rate distortion theory. Rate distortion theory meaning the compromise that we have, the trade-off that we have between rate in one hand and distortion in the other hand. Okay, we can sort of trade one for the other. Then we'll do something that is very interesting. All of this, by the way, is subject of a course that we have here at Unicamp. That's a 60-hour course. We're going to have to bring it to a 3-hour course. So it's a compression of 20, which is not bad, there'll be some distortion. Some students in the regular course say that homograph complexity is the item that they like the most. It was the one that was worth the price of admission, as they say. And because it's a totally different view on the issue of measuring uncertainty and measuring information. It's the subject that was initiated in Russia, so completely independent because of the Cold War at that time, completely independent of what was happening in the West, in the United States in particular, with the work of Shannon. And then after he published his 1948 paper, still there were some separation between the two worlds. And Kolmogorov did that at about the same time as Shannon, and from a completely different perspective. Shannon's perspective was a probabilistic one. It had to do with an underlying distribution. And Kolmogorov is completely free of that. It's computational complexity. It's algorithmic complexity. It has nothing to do with probability. And then we'll try to see how can they tie together in some ways. We'll have a monkey helping us do that job. There's a monkey typing on a typewriter or on a computer. And we'll see what the difference of what can happen. Then we have some applications. This will be very brief because I'm trying to spend most time on the very basics of this subject. We have some applications in biology and some in economics. These applications in economics sometimes draw some attention because we're going to be talking about portfolio management, how to select a portfolio of stock options or stocks in a way that you can have your money growing exponentially. You know, it's nice. Or how you can gamble also in an optimal way, even gambling on a horse race, for example, how you should put your money in the various horses. And then, for last, we'll talk about something that's still topic of very active research in this area. Perhaps where most of the research, I would say that these new applications in biology and economics are not so new, by the way, it's been around for a while, but these applications, along with multi-user information theory, that's also sometimes named as network information theory, they are where the research is happening, and there are many open problems. You know, of course, the low-hanging fruits they have been collected already, but sometimes you find an apple that's sort of you know, reasonable distance, and then we have some wrap up. Okay. By the way, any questions? Please interrupt me. A little bit of references. These are textbooks. We'll try to get most of the material from Cover and Thomas, Elements of Information Theory. It had 2 editions, 1991 and 2006. Tom passed away in 2012. Very sad event because he was really a mentor to many of us and a champion of information theory. His enthusiasm was contagious. You know, he would talk about information theory and about statistics. He had a joint appointment at Stanford in the electrical engineering department and also in the statistics department. And he would really captivate everyone. You know, he would ask, imagine the impression of finding an expression like 1 over square root of 2 pi times exponential of minus x squared over 2 coming out of the blue, coming out of nothing. And that's what happens in the statistics. So this enthusiasm, he was really something that motivated a lot of people to go into this area. Then there are a couple books that are classics. One is the book by Ash that has a new edition by Dover. Dover published both books, and this came out in 1990, but the original book is much older, and has a very nice presentation about an approach to entropy that is based on postulates, on some axioms. It's an axiomatic approach to information theory and to entropy that I think very nice. And then the book that's by Robert Gallagher. Gallagher is still around. His name was mentioned today as the inventor of DPC in Valdemar's course. He is a giant. He is a giant, and he's still active at MIT. You know, and he's still publishing a book. There's a book that's going to come out soon, and he's a fascinating person. And this book from '68 was the book that I used here at Unicamp as a student when I was doing my master's degree here from Bhagawan Spanola Lati. Lati was the professor of this course, and the book was this classic book, Information Theory and Reliable Communications. The reason why the book by Cover is more widespread now is because Cover tried to put everything in a very, very basic language, very basic concepts. And this is something that he can do like anyone else, you know, amazingly. The other book, the last one, is a very recent book that has a lot of new information. Network Information Theory came out only like 4 years ago by El Gamal and Yang Ho Kim. And this is a book that is really a must for those that would like to do research in this area, because it has many open problems and most of the action is really contained there. Okay, I'd like to mention a little bit about the IT landscape, the connection that it has with many other subjects. It's really fascinating because more and more we're discovering ways in which information theory can help in other areas. Of course, the communication theory was the original idea of Shannon because of the problem of source coding and channel coding, but it has connections with probability through large deviation theory, statistics, inference, statistical inference, mathematics. You have, in mathematics, there are some inequalities that are very important that come out of information theory. And sometimes you can prove a very complicated inequality by means of information theory with some very one-line proof. One example of that is a proof of an inequality, Hadamard inequality, proof in linear algebra that has, you know, a somewhat complicated line of thought, and it's a one-liner with information theory. Then you have economics. I mentioned the portfolio development, the gambling, biology, DNA. We are all encoded in our DNA. You know, can you imagine the idea of just breaking that code? We'll talk about some of the applications. In fact, we're very proud to have some of the main breakthroughs here at Unicamp with one of our colleagues, as I'll mention to you. Computer science, Kolmogorov complexity comes into play. Physics, thermodynamics, statistical thermodynamics. So there are a number of areas that benefit from information theory, maybe to make it better understood, or maybe to just get simpler proofs of known concepts. Okay, so we'll start with entropy. Entropy, the name entropy, of course, comes from all the way to Boltzmann. Boltzmann has in his epitaph, in his tomb, the formula S equals log of W, and Shannon chose to use the name entropy for his quantity because he realized that that was the concept that could measure the amount of randomness that there was in a particular random variable. So we're looking now at a random variable x that is a discrete, for now, discrete random variable, and that has values on a particular set, x1 through xm. Okay, so very simple. And has probabilities p1 through pm. So he realized that log of the inverse of the probability, in a way, is a measurement of how much information is conveyed by the revelation that that random variable was equal to xi. So if I find, for example, that, suppose x2 here, I find that the random variable is really equal to x2. So the amount of information that I received is proportional to log in the base 2 of 1 over p of x2. Okay? And that may be a very large number, maybe a small number. For example, if I tell you that the sun is going to rise tomorrow, very little information on that, right? Because we know that that's almost a sure event. But if I tell you that the sun is not going to rise tomorrow, that would be earth-shattering. You know, that would be a lot of information. Well, he decided to measure in uncertainty or the amount of information with the knowledge of the random variable by the average, the expectation here of this number. And then the expectation takes this form here, summation of p times the function. Okay? So that expression is a measure of the uncertainty that is built in a random variable x. And you notice that another notation for this, and it's probably more appropriate, is that's really the h of the p, or the vector of probabilities, because it does not depend on the values that the random variable can take on. It doesn't depend on that. The values can be blue, yellow, red, and so forth. Or it can be 1, 2, 3, 4. Or it can be names of people. It can be anything. What really matters is the probability with which these values are assumed by the random variable. So, even though this is a more common notation, h of x, it would perhaps be more appropriate to consider this one. In any case, there are some advantages in using this one here, because you'll see it's easier to manipulate expressions and so forth. Okay, questions so far? The book by Ash has a very interesting axiomatic question. Please.
You can prove Huffman inequality. I was wondering which Huffman inequality you say of determinant.
The determinant one, yeah, that one. And you know, in fact, in the book by Thomas and Cover and Thomas, they have that. And the paper that came out is like 1 or 2 papers, 1 or 2 pages. It's really fascinating. Okay. All right. So this is entropy, and then we can say, well, let's think of a way that this entropy can arise naturally. You know, just to give some motivation for it. It's not something that came out of the blue. In fact, as I mentioned, the book by Ash has an axiomatic approach to this, and it's a very simple set of 3 axioms. One is continuity. You know, you'd expect that the function, a good function to measure uncertainty, would be a continuous function of p. That's quite reasonable. And then there are 2. One is monotonicity. Also, if you take the uncertainty of taking one person in São Paulo at random, São Paulo has about 10 million people, so it's the uncertainty of randomly picking one person in 10 million. And the uncertainty of picking one person in Campinas, which is about 1 million. Of course, there's more uncertainty about São Paulo. Right? That's the monotonicity axiom. And then there is a third axiom called grouping axiom, which tells you if you get the information in parts, or, you know, all of a sudden, the amount of information that's conveyed is the same. For example, suppose that I find, for some, you know, special reason, or maybe a genie, that the champion of the soccer championship this year is going to be from São Paulo. And then I find out what was actually the team that won. You know, so doing it in 2 steps or in a single step, it conveys the same amount of information. So that's the third axiom. And by these 3 axioms, the only solution to measure the information is the one that we just saw, is the Shannon entropy. So it's really fascinating in this respect. But let's now look at some way in which it can arise naturally. Suppose we have a sequence of random variables. We use this acronym very often, IID, independent and identically distributed random variables, according to some p of x. Okay? And I want to know what is the probability of a particular sequence. Just pick a sequence and I take the probability. Well, by independence, I can just take this as the multiple of p of x1, p of x2, and so forth, because they're all distributed independently and identically distributed according to p. Okay, so no problem there. Then I can write this as a product of p of xi. Then I do a trick that's quite often done in information theory. There are many, you know, when we look at the portfolio selection, we're going to be doing that. You want to change things that are multiplicative to things that are additive. Okay, so one way to do this is to take the exponential function here on the base 2, and then there'll be 2 to the log of the product, but then the product can come out here as a sum. Okay, so far no problem. Now I do a little trick. I multiply and divide by n, and I take this sum, which is taking, all this sequence, all the steps of the sequence, by putting together all the elements that are the same. So just imagine you have a bunch of money, and these are bills of 1, 5, and 10 cruzeiros or reais. Okay, one way to do the calculation of how much money there is just count one by one, right? Which is what is being done over here. Another way is to take all the ones that are 1 real, the ones that are 5, and the ones that are 5, that are 10, and then having a coefficient associated with the number of them. And that's what we do here. So this ni of j is the quantity of times or occurrences of the jth result in the sequence of all these n elements. Notice that now the sum is not to m anymore, it is to n, is to m, which is the number of possibilities that you have in the random variable, okay? The alphabet, say, of the random variable. So, by the law of large numbers, and then there are two versions of that, the strong law of large numbers, the weak law of large numbers, this will converge to something. It's a probabilistic convergence, so we have to be a little bit careful, because it's not the same convergence that we have in regular analysis. So we can talk about convergence in probability, or we can talk about convergence with probability 1. Then we have this law of large numbers that say that this number here, the frequency divided by n, is going to converge to what? To the probability of xj, right? Well, and then if I put xj, what would this be? This would be minus the entropy. So it says that, and this is related to something that we'll see later, the asymptotic equipartition property, that if you take a sequence at random, that probability will be very close to 2 to minus nh, independent of the sequence. So they will all have the same probability. They will all have the same probability. And that's why it's an equipartition property, which happens asymptotically for a large n, okay? And this is something that I like to say is the DNA of information theory, because it says that you don't have to bother with the things that are not typical. You just concentrate on those that are typical, and you'll be fine. In fact, as we'll see later, what is a typical sequence? One that maintains the regularity of occurrences along the way. We'll see more about this. Okay, now, we use there base 2 in the definition, but we could change the base, and it's very simple to change the base. We could now define h sub b of x, just to have a different base in the log. And then usually we have some units associated with this different bases. The change of base is essentially log of a in the base b will change you from HA to HB. Base 2 is bits, very common. Base 10, these are not very much used, but it was something that was used to make a homage to Hartley, one of the early scientists that studied communications and this type of mathematics. But it's also called DITS in some places. The one that's very common is the NATS, the natural, the base E, the base of the natural log, because it makes differentiation simpler. It's basically a convenience. Sometimes we do things in NATS, and then at the end I say, okay, now we can do a little transfer by multiplying by a certain log to have it in bits. And then, I haven't seen this, but I think TRITS would be a good base for base 3. Good name. Okay. All right. Some examples. Let's take a random variable that is binary, okay? And it's actually not binary, it's unary, because it's 0 with probability 0 and 1 with probability 1. So imagine a two-headed Cohen, for example. It's always Cohen, okay? So what's the uncertainty about that? Well, we would expect to have no uncertainty, right? And if we plug that into the expression there, it's going to be minus 0 log 0 minus 1 log 1. It's going to be 0. And you notice that there is an indetermination here. But then by continuity, using L'Hopital's rule, we can see that the limit of p log p goes to 0, so that will be okay too. And we can, in fact, just take this as a definition. 0 log 0 is going to be 0. So there's no uncertainty because x is a deterministic random variable. Now let's look at something different. Suppose we have a binary random variable that has a probability p of being 0 and 1 minus p of being 1. Then the expression is this, and this expression is particularly important, and so it has a notation that's a different notation. It goes for small h of p, and it's a function that's just like this. It goes from 0 to 1. The maximum is at 1/2. And it's interesting because, imagine that these two possibilities were the ones that I talked about earlier. The sun may rise or the sun may not rise. There will be a very large amount of information if I tell you that the sun will not rise, but very little information if I tell you that the sun will rise. But in average, if p is like the probability of the sun, let's suppose that's 1 in a trillion, the p is very small, and the entropy will be very small too, because it's a very skewed type of average. You have a very large number, but the amount of information when you realize that the sun will rise, it's so small that brings that down to 0, and you have a very small average information over here. The maximum information you can get is if I tell you that the random variable has probability half of being A or B or of being 0 and 1. That's the maximum information. So you want to have, if you're trying to get some information from a certain question, a yes-no question, you want to have a question that would pretty much be balanced between yes and no with 50%. In these problems of 20 questions and everything. If you do something different, you're going to be throwing away questions. And in coding, basically what we're doing this, when you put a number there on a sequence, basically you're answering a question. You're saying that that's a 0, that's a 1. So you want to have some astute way of doing this balancing. Okay, so h of p is the so-called binary entropy function. Okay, now I come to a lemma that is sometimes called the information theory lemma. It's a lemma, it's so simple, but we'll see that most of the stuff that we'll see this afternoon here is really derived from this. It's an amazing consequence to say that the natural log is smaller than x minus 1, smaller than the straight line, that passes by x equals 1. And the proof is very simple. It's a Taylor series expansion with remainder. You throw away the remainder by adjusting the point where you do the sampling, and then you have it. So it's very simple. And as you'll see, most of the things that we'll see is a consequence of this lemma. Okay, in fact, very soon we'll have one. I'll now define the relative entropy or the Kullback Leibler divergence. I was in France in September, and I noticed that there is a very tense situation about calling this Kullback Leibler distance. In the book by Cover, he calls it Kullback Leibler distance. The thing is that, of course, Cover realized that it's not a metric, but in Europe, they tend to use distance as synonym of metric. So they say, oh, it's not a distance, true. So we can't call it Kullback Leibler distance. And in fact, one of the reviewers of our paper suggested that we call Kullback Leibler divergence. And then I said, okay, to settle this issue, let's just call it Kullback Leibler divergence. It really comes out of hypothesis testing, where you have the null hypothesis and an alternative hypothesis, and then you are trying to find the log likelihood ratio of this. Well, the definition is exactly this. It's the divergence between P and Q. Notice that there's a certain order here, is the expected value with respect to P of log of P over Q, which is the likelihood ratio. Okay? So this quantity has also an amazing effect on a number of things. And very often, the proof comes out to show that something is of this form. And then it's, you know, it's non-negative, as we'll see just next. You know, it's something that's always positive, or non-negative. You know, it can be zero, but it cannot be negative. So that's the Kullback Leibler divergence of P with respect to Q. So we have to maintain this order here, because it's not symmetric. And the proposition that we can derive from that lemma that we just saw is that D of PQ is always non-negative, with equality only if P is identical to Q. Okay? The proof of that is very simple. I will try not to include too many proofs because I don't want to bore you. I would prefer to highlight the applications and the way that these things can be used. But some of these proofs are so basic that are nice to. It would be a pity not to go over. Okay, just write this. First, let's consider the set of A in which X has positive probability with respect to P. I don't care about Q for now. But with respect to P, it's going to be positive, because I don't want to divide by 0. Okay? So now I can write that log of X is smaller than X minus 1. That's just the lemma. Well, let's then substitute Q over P on the expression. Then we have that. Now we multiply by P of X on both sides, and we sum over A over X in A, which has positive probability with respect to P. Then we have just that here, okay? Well, but notice that the second one here, P over P cancels, summation of Q is going to be less than 1, perhaps, right? Because Q doesn't have to have all its weight on A. But summation of P is 1, because all the events of positive probability are considered. So this summation here is going to be less than 0, right? And on the other side, what do I have? I have minus the divergence, because it's inverted here, right? So minus the divergence is smaller than 0. In other words, the divergence is positive or non-negative. And the only way in which it can be 0 is if P and Q, in other words, I have here a ratio of 1 in A, but then if it's in such a way, then P has to be Q equal to Q everywhere. So it's very simple proof. Okay. So the Kullback Leibler divergence is very useful in information theory, but it's not a metric. Okay, and or a distance for those that consider that as a synonym. And it's also not symmetric. That would be one of the constraints, one of the requirements to be a metric. And the other one is to satisfy the triangle inequality. It also doesn't satisfy the triangle inequality. But it's an amazing measurement that we can have to compare distributions, to see how close one distribution is to another. It's extremely useful. Okay, one of the applications that we can have of that lemma, by the way, this lemma here is the one that's usually called the information inequality. Information inequality. But it's really a consequence of the lemma there of log of X being smaller than X minus 1. It's a direct consequence. Okay, so one of the applications, suppose Q is the uniform distribution, okay? And P is just any distribution. Now I take the dP of with respect to Q is positive. Then here's the expression. Now we can write this by passing the Q to the other side as this, but Qi is 1 over n by assumption. Okay, so we have that. That can be placed outside, and log of the sum of P is 1. So on this side here, I have minus entropy, so that's going to be minus h of P. And here I have minus log of n because of the inversion here. So inverting again and inverting the sign of the inequality, I have the h of P smaller than log of n. In other words, the uniform distribution has maximum entropy. That's a simple consequence of the lemma and of the fact that the divergence is always non-negative. Okay. Now, to extend the concept of entropy, we need to look at something a little bit more involved. Let's look at joint distributions of two random variables, x1 and x2. Okay? And in this diagram here, I have the joint distribution in place here. So I have all the elements of y and elements of x. And in each position here, I would have the probability associated with the pair xi and yj. Okay? Now, that's the joint probability. The joint probability has all the statistical information that I need to characterize the behavior of the random variable. Okay? Well, there are some things that I can take from the joint probability. There are functionals. There are partial views of that joint probability. For example, I could take the sums over the columns or the sums over the rows of this matrix. Well, if I do a sum over a certain row, I'm going to get the probability of y1. And if I do a sum over, say, the first column here, I'm going to get the probability of x1. In other words, these probabilities here that are after I do the sums by columns or the sums by rows are the so-called marginal distributions. These are the distributions associated with one of them, but not the other. Basically, what I have to do is to sum over y, sum the joint over y, and I get p of x. And I sum the joint over x, and I get p of y. So very simple. Notice that these guys here are determined by the joint, but they don't determine the joint. You know, the opposite doesn't go, okay? Unless you have some additional information. For example, a little bird comes and says, they are independent. And then you say, oh, then the joint is the product, okay? All right, then you have the conditional probabilities. Conditional distributions are, again, from the joints, I can get the marginal, and if I divide here, I'll have the conditionals using Bayes' rule. You have seen it in many forms. Essentially, the joint determines everything that you need to know, marginals and the conditionals, and the opposite is not true. Okay. Now we can associate entropies with this distributions. For example, we can have the joint entropy, and the joint entropy is essentially the sum. Now it's a double sum here of x and y. I could have represented it with two sigmas, but it's more efficient to just go like this, realizing that it's really a double sum of p times log of 1 over p. Notice that there's no new concept here, because I could think of x, y, the pair, as being a double variate z, a random variable that is really formed by a pair. So it is essentially the same concept, just extended a little bit. But the condition entropy, it has something new, because when we do the conditional entropy, we first have to consider doing the conditioning on each of the given values here, and then take the expectation. Or in another way, we can just think of the expression. Notice that this is the joint distribution here, and I'm taking the log of 1 over the conditional here. So the condition doesn't go on this side. It goes only over here, because I'm taking the expected value of log of the conditional. But to do that, I need to have the joint here. Okay, so this is something that in tests people sometimes make mistakes and so forth. One has to be a little bit careful about this. Okay? When dealing with continuous random variables, sometimes it's very dangerous to go for the conditionals, because you often have divisions by 0, and you have something that happens and it's not so good. So it's best to stay with the marginals and with the joints. They're safer, okay? And then we have something that is, again, a very important result. And it also almost comes from the definitions. Is the chain rule. It's like, you know, peeling like an onion. You know, you remove the uncertainty layer by layer, okay? So you have, for example, here, the entropy of x and y, the joint entropy of x and y, can be written as the entropy of x plus the entropy of y once you already know x. So that's the conditional on x here. Or you can peel it the other way. You can write it as the entropy of y plus the entropy of x once you already know y. Okay, so these two things are expressions for the joint entropy, and they are essentially the chain rule. Many of the problems that we have in homeworks and everything is essentially an application of the chain rule that gives you the solution. And my suggestion is that you do it for homework. The proof of this is very simple. It's simple algebraic manipulation on the expressions that we've seen before. A corollary of this is the conditional form. If I have a given z, I just carry it all the way on everything. By the way, notation here, when I say that's given x and z, there is no particular ordering here. It could be z and x. It's just whatever is already known at that point. So that's the entropy of y given x and z, or z and x. Okay. Now comes the most important of all of these expressions, and you'll see why it's the most important, because it's associated with a number of theorems that we'll see. The first theorem of Shannon in data compression, it's expressed in terms of entropy, but then if you look at the grand picture in terms of rate distortion theory, it's really expressed in terms of a mutual information. If you look at the capacity result, the capacity of a channel, it's expressed in terms of a mutual information. So it's quite a very important entity, and that is the amount of information that relates x and y, two random variables. What does one tell about the other? Okay. Well, the definition that we choose is this one. The Kullback Leibler divergence of the joint distribution P of xy and the product of the marginals P of x times P of y, that divergence, which is expressed here, is the mutual information. Okay, so it's very simple. It's essentially this. Notice that the order is, here's the joint, and here is the product of the marginals. In other words, we are assuming as the null hypothesis that the distribution is really from the joint. But I'm testing the hypothesis. Maybe it's from the product, or maybe it's independent. Let's check. Well, if you have some assumption to go away from your assumption, it's not just any evidence that's going to take you away, right? It has to be some strong evidence. And maybe the decision is still wrong. You know, it might be that it would be true, but since the null hypothesis has some prevalence, you may be stuck at the null hypothesis. That's part of the hypothesis testing. You have to have a strong evidence to change your mind. So you have to be a little bit conservative, so to speak. Okay, so now this then is a divergence. If it's a divergence, then it's non-negative, right? It cannot be negative, which makes a lot of sense. I cannot have a negative information about something, you know. At the most, my information doesn't help anything, you know. And so that is the expression, you know, if we write the divergence as the, now I put in two sigmas here just to make it very clear that it's a summation over x and a summation over y, the two alphabets of these random variables. And here is the probability, which is the joint, with respect to the log likelihood of the joint with respect to the product of the marginals. Okay. And as I said, because it's a divergence, it's non-negative. And equality will happen only if the joint is the product, which happens when the two distributions are independent. So if and only if x and y are independent, we'll have the mutual information being 0. Okay, the proof is like one line, as I mentioned here. Symmetry. Symmetry is also trivial because P of x, P of y is the same as P of y, P of x. There's nothing that really makes this asymmetrical here. Notice that it's not symmetry that we have in the original general expression for the Kullback Leibler distance, because here I'm particularizing for this two. So it's this, in this respect, it is symmetry. Okay. Now let's look at mutual information and entropy. How can we express this in terms of entropies? Well, here's the expression that we had. It's the double sum of P of xy times this log. Now, each of these terms here in the log is associated with a particular entropy. This one here is associated with the joint h of x, y. And the minus here comes from the fact that it's in the numerator. Right? Notice that here is the proper joint distribution here. Now also, this p of y here, it's in the denominator. So that's where it should be placed. But there is a p of x here. And there's, why would this be h of y? Anybody could answer that? If you sum over the x's, you get p of y. So you do the first summation here over the x's, and you get p of y. And then you have summation of p of y log of 1 over py, and that's the entropy of y. Similarly, you have here the entropy of x. So this is essentially, from above, we can get this separation here from the property of the log of the product being sum of the logs. Okay, and then using the chain rule, but in a reversed way, or we do it here, we cancel one of these terms and we get these two expressions. Both of them coming from the chain rule in the two alternative forms, depending on how you start to peel the onion. You can have these two expressions here, and they are very much revealing. They say the following. They say that the mutual information between x and y is the uncertainty of x minus the uncertainty of x once I already know what's y. So the difference is what y told you about x, right? And essentially that's what we're saying here. It's the residual information after you know the result of the other variable. And it's interesting that this is a symmetric thing. So if x says something about y, y says the same amount of information about x. And that is more or less depicted in this Venn diagram here. And this Venn diagram is very nice, works very well, but I have to give you a caveat here. It works well for two random variables. If you put a third, then there's some things that are not even defined. And maybe you could try to make a new theory for that, but people usually don't go for anything more than two. But for two is very nice. Now you have here the associated entropies of x and y, okay, which is these balls. And once you take a bite out of the other one, the amount that is in common is the mutual information. And of course it's symmetric, right? It's, once you see this picture, it's clearly symmetric. And here you have the remaining, the remainder here is the conditional of x given y. You still have uncertainty about x, even though you know y. And here you still have uncertainty about y, even though you know x. Okay. This brings another very interesting result that's very much used in small proofs. This type of information theoretic proofs that happen to be very often one line. Conditioning reduces entropy. So maybe the information, specific information about some random variable will increase uncertainty in some way, but that can only happen for specific values of that knowledge of that random variable. In average, it's always going to decrease or at least not reduce the amount of uncertainty. So this is on average, knowledge of y cannot increase the uncertainty about x. Why is that? Well, because h of x given y is always going to be smaller or equal to h of x. Proof of that is one-liner. Just write the information, mutual information of x and y as this. I know that this has to be non-negative, so that gives the result right there. Just bring the conditional to the other side. Okay? So everything of this so far came out of that lemma, log is smaller than x minus 1. Everything. It's really something that has an amazing consequence, even though it's like a butterfly effect maybe. It's just a little thing. Oh, interesting. The first time you see, oh, this, what is the worth of this? And, oh, of course, log is smaller than the line. Big deal. Well, here's the big deal. Sometimes entropy is called the self-information, because if you look at the mutual information between x and itself, it's going to be the entropy of x minus the entropy of x given x. But the entropy of x given x is 0. Right? If you know x, there is no uncertainty. So that's 0. So this type of thing we can use very often to take a complicated expression and simplify it. So this is essentially the h of x, and that's why it's called the self-information. Okay, this is another result that's very interesting, and I give you here in a simple format because there is a more general expression. This is the data processing inequality, and the more general expression is associated with Markov chains. If you have a chain of random variables, and there is conditional independence between the two extremes given something in the middle, then you have this nice result called the data processing inequality. For now, we'll do a simple form, but essentially the idea is this. Passing on information can only decrease information, right? So I have some secrets, and I tell my friend, oh, here's the secrets. And my friend is going to go and tell somebody else. There might be some distortion here. So there's no way that the person that gets it at the end will have more information than it was already built in the intermediate message. In other words, putting this in terms of a proposition, the mutual information between x and y has to be larger, or at least equal, to the mutual information between x and some function of y. You know, here is a function of y. You know, is the passing on of the information. Okay, so that information here cannot reveal more about x than y was already doing. Okay, and the proof of that again is very simple. You just write it like that. Then I do a little trick here. If I have y, I have phi of y, because phi of y is a deterministic function of y. So I can include that in the conditioning here with no penalty. This is equality here, right? Now, if I drop the y, I'm dropping conditioning. And conditioning, if I drop the conditioning, it's going to raise the entropy, right? So this is going to be a larger number, but because of the minus sign, this then is smaller than that, and that is the mutual information between x and y, and phi. So conditioning reduces the entropy is the reason for this inequality here. And as I said, this is a simple form of the data processing inequality. Okay, now we're going to take a quick review. We're going to go back to the primary school. Lots of fun, just to relax a little bit and talk about convexity. Okay, convex sets. All these sets are convex. And these sets are non-convex. You know what I mean, right? If you take 2 points, and if you associate a line between them, the line cannot cross outside the set. If it does, it's non-convex. Well, fine. Now let's take this concept to functions. A function is convex if the set of points above its graph is a convex set. Okay? So the definition is very simple. The set of points above its graph has to be convex. So examples, x squared, exponential of x. And mnemonic, that sometimes people have confusion between convex and concave. Okay, very simple. The exponential is convex, and there is a little exponential here at the end. Okay, so nobody will forget more what's convex and concave. Okay. All right, what is concave? Well, a function is concave if minus f of x is convex. Also very simple. Examples, log, the minus modulus function, they are convex. And some of them are not convex or not concave, like x squared. And some of them are both. Actually, there is only one family of functions that are both, are the linear functions. Okay? If a function is convex and concave, then it's got to be linear. End of the time? All right, okay? Okay, so we come to something that is really very, very important. And, you know, often we have this course in electrical engineering. The course is usually given in electrical engineering. But there are people come from mathematics, from computer science, from physics, from administration. There are people come from everywhere. And lots of people also from electrical engineering. And I asked them, do you know Jensen's inequality? And often they don't know, very seldom they would know. Usually when they do, they come from the Mathematics Institute. But it's an amazingly important inequality. So amazing that Tom Cover had this famous phrase. Of course, he was joking, but he was saying, I don't make many proofs. But when I prove something, usually I use Jensen's inequality. So that's how important it is. It is essentially this commutation between expectation and the function. Okay? So the expected value of a function that's convex is going to be greater than the function evaluated at the expected value of x. Proof by induction. If the second derivative of the function exists, we can use Taylor series. It's a very simple proof. But in any case, I think the mnemonic is essentially that the chord where the expected value of f of x would be is above the arc where the f associated with the expected value of x would be. Here's the expected value of x, and then f of e to the of e of x will be here, and the other one will be here. So, then we don't have to worry about the direction if it's concave or convex. Of course, if it's concave, it goes the other way. This is also extremely important and can be used to demonstrate many concavity results between the Kullback Leibler distance, between the mutual information with respect to different arguments. And one way to prove the concavity of the entropy function is using Jensen's inequality, but I chose here to prove something, to use something even more basic to show that the entropy function is a concave function of the argument of the distribution. And here's the proof. Again, it's a simple proof. You just take x1 to be distributed as a certain p of 1, and x2 distributed as p2. Okay? Now take an index theta between 1 and 2 with these probabilities, lambda and 1 minus lambda. So let's define z as being x sub theta, so it could be x1 or x2. Then z is distributed as, according to this convex combination of p1 and p2 with parameter lambda, right? Now, since conditioning reduces uncertainty, here is h of z is smaller than h of z given theta, because conditioning reduces entropy. All the way from that lemma there, that log is smaller than x minus 1. Now, what is the entropy of z? Well, it's the entropy of this distribution here. And what is the entropy of z given theta? It's going to be h of p1 with probability lambda and h of p2 with probability 1 minus lambda. This is essentially saying that h is a concave function. So one consequence is if we mix two gases of equal entropy, it results in a gas with higher entropy. Again, second law of thermodynamics coming into play here. So I'm sure that Boltzmann was happy when he realized that Shannon was pursuing these things after his work. Okay. Notice that we could use some other things, but again, we're looking at that very, very basic lemma that we had in the beginning. There are some additional topics that I'm not going to go over because of time, but there's the log sum inequality that's very powerful, that can help also in showing, in fact, that the convexity of d pq with respect to the pair pq. And this is something very interesting too. The mutual information is a function of the joint distribution p of xy, which can be expressed as p of x times the conditional distribution of y given x. And this will be a concave function of p of x and a convex function of p of y given x. That's why sometimes you try to maximize the mutual information, sometimes to minimize, because it lives on a saddle point. It's one, depending on the dimension that you're looking at, it may be a convex function or it may be a concave function. Okay? So additional topics that could be looked at in the same chapter of the book by Shannon. Markov chains, the data processing inequality in its full expression, sufficient statistics. And this is something that's very important. Funnell was a colleague of Shannon at MIT. They all worked there as professors. And Shannon needed some inequality to prove the converse of his theorem. And Funnell is the one that came up with this inequality. So in most converses, Converses is the part of the theorem that says that if the rate is above capacity, you cannot have small probability of error. For that part, usually we need funnels inequality. Okay? And sometimes the converses are more difficult to go about because sometimes there is no available funnel inequality for the problem. Okay? For example, in the interference channel, when you're trying to decode from interference, you don't have any obligation to decode the interference. So there is no associated funnel inequality with respect to the interference. You can only have the funnel inequality with respect of the things that you want to decode. But the interference you may or may not decode, so it's sort of loose. And that creates some difficulties. Okay, now this thing looks like an egg, and it's not by chance. It's because the AEP is the birth of information theory. Is I call it the DNA of it. Okay, and essentially it says the following: suppose we have a series of random variables here, and they are IID, okay, independent and identity distributed, according to some P of X. There will be some sample space here, which is a set of all possible sequences of results. Okay, but within the sample space, there is a certain set called A epsilon. This is a standard notation. It's the set of typical sequences. The epsilon is associated with how much precision you want in these statements here. Now, if you make the epsilon smaller, of course, the set will be a little bit tighter, but you'll get to a point that it cannot go below. And this set has some very interesting properties. First one is that the probability of this set is essentially the whole probability. It's greater than 1 minus epsilon, epsilon being a small number. So in other words, all the stuff that is in the egg white here doesn't have much probability. Doesn't happen very often. Okay? You don't have to worry about it. If you do a coder that doesn't treat that, you're probably not going to have a problem. If your stock portfolio doesn't look at that, very little chance that you're going to be losing money. Most likely be making money. So the probability of everything is essentially here in this A epsilon. And then there are two things that are sort of complementary here. And what they say is that everybody here is a subject of God. Everybody here is the same. There is no preference. They are all the same. Okay? In other words, they all have essentially the same probability. What is the probability? It's 2 to the minus nh. Okay? And how many of these are here? Well, if you have that probability and they are uniformly distributed, you would have the cardinality of this set is essentially 2 to the plus nh. Complementarity, right? And again, this can be made precise here. And so if you are trying to, for example, do an encoding for a sequence of random variables, if you look at those that are typical, this set here is called its set of typical sequences, you would be fine. What is a typical sequence? Well, given it like that, it may be a little bit obscure, but I'll give an example that try to simplify. Suppose we have a biased coin, okay? And that coin has a probability of 0.9 of giving a result that's head, and 0.1 of giving a tail, okay? And I have independent throws of this coin. 1,000 long sequence throws or coin tosses. What would be a typical sequence? A typical sequence would be one that has approximately 900 heads and approximately 100 tails, right? So you'd like to bet on the typical sequence, right? But the most likely sequence of all is not in this set. What is the most likely sequence in this outcome? Is all heads, but it's not typical. But it's only one, right? So even though it's only one, even though it has the highest probability of all, it's over here in the white space, okay? Not in the yolk. And the yolk is where the life is. Here is just food for thought, okay? All right. So it's best to bet on the typical set. And essentially, information theory is this. That's what Shannon realized. That when you're transmitting something over a channel, you don't have to worry about the stuff that doesn't happen, or doesn't happen very likely. You just take that space. And consider also, when you have some conditioning, you look also what happens with the conditioning, but again, looking at the typical sets. Okay? So if you restrict to the typical sets, everything comes out almost like automatically. Okay. The concept of entropy that we saw for random variables can be extended to random processes. And then we can talk about the entropy rate of a process. Okay? So, usually these definitions here, and it's not trivial to show that they are essentially the same, but it's true. If we have a collection of random variables, notice that now they don't have to be independent or identically distributed. They are indexed here with their particular distribution. But the entropy rate of a certain process, now considered here as a collection of random variables, it's going to be the same if I consider the entropy of the present given all the past. That's one definition in bits per symbol. Or if I just take the entropy of the whole sequence divided by n, because I'm considering the entropy in terms of bits per symbol. Okay? So these two expressions are can be shown to be equal. These two limits are the same. Okay? And that is the definition of the entropy rate of the process. Okay. Okay. Yeah.
But I think there is an hypothesis there. At least I remember something about
ergodicity. Yeah. There is some conditioning.
In the course there was an exercise that precisely that.
Of course. Yeah. This is not for a general random process, but it's some process that has some type of regularity. Ergodicity, for example, would take care of that. Okay. Good point. Okay, now we look at, so that's already chapters 2, 3, and now we are chapter 4 of Tom Cover, data compression, source coding. Source coding is something very interesting, and we're going to revisit it when we see rate distortion theory. And in fact, here is a source of information, and there is an encoder that looks at the source and puts out an index. An index is just an integer, for example. And here the decoder reproduces something that he can do from the index. Okay, so pretty much it's like this: you have a source space, and you want to cover this source space with areas of representation. Okay, so it's almost like we are electing a representative in a particular neighborhood. So we have a neighborhood here, and we elect a representative. So that representative can be characterized by an index, just representative number 245. And then that will be, everything that has to be with that neighborhood will be looked at from the perspective of that point there. So that's going to be a reproduction. Notice that there will be some distortion because maybe the point was not right there, was somebody else was being represented. So that representation is not going to be with a lot of distortion because we are still in the neighborhood here. So the feelings and the sentiments are alike, right? So that's one way to think about this. Another way to think about this, and it's perhaps more appealing, when we go to a restaurant, and we really really would like to order a particular sandwich with 300 grams of this, and 2 leaves of lettuce, and 1 piece of tomato, and a little bit of radish, and this and that. But maybe it's not in the menu, right? In the menu there's something that's an approximation. And that's this sandwich number 5. So I would like to have sandwich number 5. So here's the sandwich that comes out. And it's very close to the sandwich that you'd like to have, but not quite. So that's, this distance here is also called quantization error. Okay? So of course, maybe you would say, oh, but the restaurant doesn't have too many sandwiches. There are only 5 sandwiches. Well, we used to have a pizzeria here called Team Ball, which is famous for those that were studying here in the 70s. Team Ball had something like 250 types of pizzas. And you really could have a very close pizza to the one that you would conceive in your best dreams. Okay. All right, but we're going to take a first look at this, not in full generality, but just looking at a very simple code. And a source code X is a mapping from an alphabet of a certain source to a finite sequence of D-array code alphabet. Okay, D could be 2, could be 3, could be some given alphabet for the code, which is different from the alphabet for the source. Just for example, suppose you have a source alphabet, A, B, C, D, E, and the code alphabet is just a binary alphabet. And then we can have the code for A is going to be 0, 0, code for B is going to be 0, 1, code for C is going to be 1, 0, code for D is going to be 1, 1. Well, and the code for E is 0, 0, 1. Notice that, there is a prefix here. So that says that this code is not a prefix-free code, or is not instantaneous. I cannot look at the code word, and say this is A or E. Because if I start looking at this 0, 0, I have to wait until I see something else, and then I see a 1, oh, this is an E. Or if it stops, no, it's an A. Okay, so this attribute of being instantaneous is very useful. Okay? It may not be necessary, because all we really want is to decode a particular sequence in a particular way. You know, you want to have uniquely decodable codes. They don't have to be necessarily instantaneous. But if they are instantaneous, it's a very interesting practical advantage. And there is a very nice result that shows that there is no extra cost for them to be instantaneous. They could be instantaneous. They have to satisfy the same inequality for being instantaneous or being uniquely decodable. Okay, so an instantaneous code or a prefix-free code is essentially a code that has no code word is a prefix of another code word. Okay, it's also called a self-punctuating code because you know the point of the end of each code word without having to look ahead. Okay, so you can add commas between the code words without looking ahead. So looking at classes of codes, we have here all codes, and some of them are singular codes. Singular codes are those that are not one-to-one mapping. You know, they associated the same code word with two different symbols, and so sometimes they are not very useful. So the non-singular codes is a subclass here, and within those you have the uniquely decodable codes, and within those you have the instantaneous codes. Usually we tend to shoot for instantaneous codes because of these practical aspects that I mentioned. Okay, so here we have a number of examples of codes, of binary codes. Suppose the source alphabet here has these values, the symbols, A, B, C, D. I avoided numeric here not to confuse with the code alphabet. Here's a singular code. Look, 0 is code word here for A and C, so that's not very useful. Here is a non-singular code, but not uniquely decodable. Okay, why is it not uniquely decodable?
0, 1, 0 could be A.
Exactly. You do not know that sequence how to parse it appropriately. This one here is uniquely decodable, but it's not instantaneous because you have a prefix here. 1, 0 is a prefix of 1, 0, 1. And this one here is instantaneous and uniquely decodable, and of course everything else, okay? So we want to have a small average code length per source symbol. And that, of course, depends on the source distribution, on the distribution of these symbols here. There is some source distribution that we haven't talked about, but that's important in characterizing what is the length of the code. So here we have, now with the proper association of a distribution here, or the probabilities of A, B, C, D, and we have a number of codes here. We can compare it. This is a very simple binary code. Since there are 4 elements, we can just take the binary representation here of 0 through 3. Okay, and that's a fine code. It's instantaneous code. In fact, every code that has constant length is instantaneous because you get to the length and that's the end of the code word. It has something that's not so nice about this. What is it? Expected length is 2 bits per source symbol, right? And typically in source coding, this area sometimes is also called entropy coding. No, you're not admitting any type of distortion here. You want to have a code that represents exactly what you had. So in entropy coding, the compression factors are not very large. You cannot expect something like a compression factor of 10 or 20, as we see in source coding of, for example, TV signals and audio signals, because those are layers of compression. We'll talk more about that when we see rate distortion theory. But this layer in which you admit some type of distortion is the quantization part of it. That can have very strong effects on the rate, and you can get very good compression rates. But once you are at the point when you want just to replicate exactly the same thing, or called lossless compression, then all you can do is to associate smaller code words with those symbols or elements that are more frequent, and longer code words to the ones that are more rare. Essentially, that's what you do. Okay? So essentially, that's what we're doing here. We're taking this symbol A here that has probability 1/2 and giving it a very simple code word, only of length 1. This is also called a comma code because the 1 is used as a comma. Okay? So you have nothing and a 1, 0 and a 1, and so forth. This is a comma code. And it has an average length of 1.875. And then this third code here, which is kind of nice because you notice that it has, well, this is also a very nice probability distribution because it's called a dyadic distribution. In other words, all the probabilities are powers of 2, and we're using a binary alphabet, so it makes it simpler to have the power associated with this minus it equal to the length of this. So this is also called a Huffman code. This is a Huffman code for this source, and it has minimal average length, and that's 1.75, which in this case happens to be the entropy of the source. Sometimes it's not going to be equal to the entropy of the source. Why is that? Because sometimes there is some rounding up, right? So you cannot have the probability associated with the length as being the log of this. Okay? So you may expect that there will be some excess rate, but the one code that has the minimum excess rate is the Huffman code, and we'll see how it's constructed in a minute. Actually, in 24 hours. Because it was a problem that was open for some time. You know, Shannon and all those guys in 1948, they started looking at this like crazy. So, oh, there is this. Well, we need a proof for the converse. And then Funnel came up with the Funnel's inequality. And this stayed around for about 4 years. In 52, I may not be precise here because 52 is when the paper came out by Huffman. And usually the paper comes out 1 or 2 years after it's conceived. But Huffman solved this problem, and he gained instantaneous fame for being the owner of the optimal codes for representing a random variable when you know the distribution. Okay, I remember that at Stanford once we had a presentation, a course given at in the summer by Rissanen. Rissanen was working at IBM in the Almaden Research Center. We are just coming to the end of the session here, so I'll just count a little bit of anecdotes here. And Rissanen, so he was working there, he was invited by Cover to give a course, special course in coding theory. And he was talking about his arithmetic codes. Okay, at that time, no one knew about arithmetic codes. And he was saying, this code is better than Huffman. And people were looking at him and said, but Huffman is optimal. What is he talking about? I mean, this guy has got to be a little bit crazy or something. And, well, sure enough, his code is extremely useful and really prevalent. And the reason is that there is some problem about Huffman. You need to know the distribution. Okay? And the arithmetic codes sort of learn what's the distribution. It can work in an adaptive way, and it can be what is now called the universal coding. You don't know what's the distribution of the source. You just put a code there that learns that distribution and then works from then on, works with in a very efficient way. Of course, in the beginning, in learning, it's going to be inefficient. Everybody has had the chance of putting a file through compress or through zip, and then the file became larger. That's because the file was not too big, right? And then in the process of trying to create a dictionary,
or it was too random.
or it was too random, then there is no compression that you can do. So yeah, in any case, don't expect compression factors of more than 3. Usually it's between 2 and 3 when you want to have lossless compression of this kind. Okay. All right, so maybe this is a good point that let's go on a little bit more, because tomorrow we're going to need time too. So this is the famous craft inequality. And there is an equivalent of this called the Karush inequality that applies to codes that are uniquely decodable. And it's the same inequality. So they both have to pay the same price. So why not have an instantaneous if I have to pay the same price as a uniquely decodable code? So it says the following: any instantaneous code over a code alphabet of size D with length L1, L2 through Ln must satisfy this inequality. This has to be smaller or equal to 1. For code 3, for example, the one that we had before, L1 was 1, L2 was 2, and the two last ones had length 3. Then we have D was 2, right? The size of the binary alphabet. So 2 to the minus 1, 2 to the minus 2, and plus this is equal to 1. So it meets the inequality with equality, and that's okay. Usually that means that it's an efficient code. You know, if you have that equality there in Kraft's inequality. Okay, this I think we can just state, and then let's see how much we have here from the other side. Okay. I guess we can go a little bit more. Okay, the first Shannon theorem. That is one of the results that he had in that 1941 paper. He showed the expected length of any instantaneous D-array code of a random variable has to be bounded below by the entropy of the source. Okay? So you cannot have a length that's greater than, that is smaller than the entropy of the source. And that's the entropy with respect to the base, the D base that's being used for the code. Okay? Very often we're going to be using base 2 because the code will be binary. So the proof of this, it's interesting because we can expand L, which is the length, minus the entropy. Okay? What is the L? L is the average length, okay? The expected length. So that's summation of Pi Li. That's exactly this. And here's the entropy. Okay? Now, Li can be written as D2 minus log of Li. We just invert the exponential with the base D and log of the base D. And we can write that as L being D to the log of L. Okay, just the famous use of the exponential and the log, trying to make something that's multiplicative into additive. And essentially what I have is that this expression with very simple manipulation can be expressed as the Kullback Leibler distance between P and R, where R is going to be this auxiliary distribution here of D minus L normalized by C, and C is the sum of the D minus L. So that's the sum that's in the Kraft inequality. That has to be less than 1. Okay? So we just take this Ri here, and we can express this in this format. Notice that we introduced C twice. One here, and the other time in the R. Okay? So this is just a simple expression that you can achieve. I would recommend that you try to get this. It's very simple. But now notice this. C is less than 1 because of Kraft's inequality. So this term here will be positive. And this term here also has to be positive or non-negative because it's a divergence, right? Then this has to be non-negative, right? L minus H has to be non-negative. With equality, with two conditions. If P is exactly satisfied by the associated distribution from the L's, which is this one here, and C is 1. In other words, the code meets Kraft's inequality with equality. Okay? So those are the conditions for it to achieve H. Typically, a code will not achieve H, will be a little bit off. And Shannon proposed, this was before Huffman, because between 48 and 52, people were working like crazy to get the optimal. What is the optimal code? And then Shannon proposed, okay, let's have this particular code here. We just take the log base D of 1 of pi, for the probability, and we round it up. Okay? So then we can find a suitable code word of this length, because there will be enough code words in the code space. Since I'm rounding it up here, there will be enough code words to meet the Kraft inequality bound. Okay? I don't want to have very small lengths, because then I may go over the Kraft inequality bound. But if I have long lengths, they add small terms to this sum here, and they don't upset the bound. Okay? So it's easy to get something when you round it up. If I round it below, I probably would not get an appropriate code word. But rounding it up is not a problem. So this is not a problem. And this satisfies, it's easy to show, that the length is going to be between the entropy and the entropy plus 1. And one way to go about this that can be efficient is you take a sequence of random variables, and then you apply the code. And then when you divide by the number of random variables, that one will be divided by all. So that excess rate there will be shared among n symbols, for example. So you can get closer to the entropy by doing it in, as they call, the extension of the source in bunches. Okay, then we come to the end. Huffman's going to be 24 hours from now. And I'll give you a simple explanation here of how to construct Huffman Code. It was really amazing that this guy, managed to find this scheme that may not meet the entropy bound, but it's the optimal scheme among all schemes. Thank you very much. See you tomorrow. Questions? Are there? We have 1 minute. By the way, please contact me also anytime you'd like. There is a question here.
Why is it called a divergence?
Divergence is because it's the separation between a distribution and another. In hypothesis testing, you are really thinking of a particular distribution, and then it may be that the sample you have is showing something different. So it diverges from that original expectation, the original hypothesis, the null hypothesis. Right. Okay. Yes?
Yeah, imagine actually finding the information we had a intuition that it should be positive, right?
Yes.
Has anyone tried to define something that's negative, for instance? Has anyone tried to define lies in information theory?
Lies?
Lies, not true.
I see. In other words, mischievous information. Yes, I think that would be interesting. That would be a new theory, Usually information theory is based on 3 main applications. If we look historically, of course, now I mentioned in my first slide that you have biology, economics, all these things. But in the beginning, it was really data compression or source coding, channel compression or channel coding. I'm sorry, not channel compression, channel coding. Coding for errors in the channel. And the third one was cryptography. And cryptography deals with these things. We may have an enemy that's malicious. And I always try to stay away from that because I prefer to fight against nature. Because nature may be very complicated, but it's not malicious. Thank you.